Module 2, Part 3 covers linear inequalities and two variables. Please make sure you are completing the matching guided notes as you go through this video. So, before we work with linear equations and two variables, and their graphs are aligned, like this first linear equation here of y equals 3 halves x plus 3. Now we're going to be working with linear inequalities. So instead of an equal sign, they're going to have any of those four inequality symbols we've seen before. So an example would be y is less than or equal to 3 halves x plus 3. You notice that the line has the same slope, but what's different is we have shaded where it's less than or equal to. We've shaded below the line, right? So before, in a linear equation, the solutions was every single point on the line. Now it's every single ordered pair that makes this a true statement, right? All the points that justify the inequality. And it's going to be way more than just the line. It's going to be half of the plane. We call this like a half plane. So let's practice to see when we can tell if a solution, if an ordered pair is a solution or not to a linear inequality. And like I said, they use all four inequality symbols. We could have less than or equal to, greater than or equal to. So if I gave us the linear inequality 5x plus 4y is less than or equal to 20, I want to determine whether these ordered pairs are solutions, and I'm going to do that by substitution. Here are my x's and my y's, right? So I've got 5 times 0 plus 4 times 0 is less than or equal to 20. So I get that 0 plus 0 is less than or equal to 20. Is 0 less than or equal to 20? Yes, this is a true statement. So that means 0, 0 is in our solution. It's not our only solution, it's one of infinitely many solutions, but this ordered pair makes this inequality a true statement. And I'm sure you could think of some other ordered pairs that would make this inequality a true statement. Like for example, maybe 1, 1 or 2, 2, right? Because 5 times 2 is 10, 4 times 2 is 8, that's still less than 20. You could even get creative, get some negatives up in there, right? There are infinitely many solutions. Next, let's check if 6, 2 is in our solution. I've got 5 times 6 plus 4 times 2 is less than or equal to 20. That gives me 30 plus 8 is less than or equal to 20. I hope we can already see that 38 is not less than or equal to 20. This is false, which means that the ordered pair 6, 2 is not in our solution. The best way to visualize the solution to a linear inequality is to graph them, right? So we know that the graph of a linear equation, a line, is all points that satisfy that equation. Similarly, the graph of an inequality is the set of all points that satisfy the inequality. So we're going to have to shade either above or below our line. Quick note, our line might not always be solid. Our line might not always satisfy the inequality, and that's when we have strictly less than or strictly greater than, and we'll have to do something else. So our steps are: step 1, graph the corresponding linear equation. If I had y is less than 2x plus 1, we graph our y-intercept, we graph our slope. Now, because it's strictly less than, the points on the line are not in our solution set. So we don't draw a solid line, we'd have to draw a dashed line. We do a dashed line much like open dots, like when we used open dots when we were working on in one variable, those endpoints weren't part of our solution. This means the line is not in our solution set. And a solid line, which we would use for less than or equal to or greater than or equal to, that means the points on the line are in our solution set. Next, what I always do is I choose a test point on one half of the plane, and I substitute that in to test if that half of the plane is going to be a part of our solution set. Do not choose a point on the line. Do not choose a point on the line. My favorite point is the origin. It's the easiest to do math with. You substitute in zeros, x's and y's cancel out. If a true statement results with our test point, we shade the half plane containing the test point. If a false statement, you have to shade the other side. So we're going to do 3 examples of this to make sure we know what we're doing. So step 1, let's graph the following. I have to rewrite this or it's going to drive me crazy. 3x plus 2y is greater than or equal to 6. So what we need to do first is go ahead and solve this for y so we can see our slope and our y-intercept. I'm going to subtract 3x from both sides. 2y is greater than or equal to negative 3x plus 6. I'm going to divide both sides by 2, remembering that if I divided by a negative, I would have had to flip the sign. But since 2 is positive, I do not. I get negative 3/2 x plus 3. So I'm going to go ahead and graph my y-intercept, which is 3, and my slope is negative 3/2, so I'm going to go down 3 over 2. This is greater than or equal to, so the points on the line are part of my solution. So I'm going to go ahead and connect all of this with a solid line. And now I need to pick a test point in order to figure out if I have to shade above or below the line. I'm sure you might be able to guess, but sometimes I think it's best to test so you can make 100% certain. I pick my test point to be my origin. It's the best test point because everything cancels out. Another good one would be 1, 1, right? Math is easy. So let's substitute that in. You can substitute it into the equation that you solved for y or your original equation. I always substitute it into my original equation in case I made a math error. So instead of having 3x, I've got 3 times 0 plus 2 times 0 is greater than or equal to 6. I get 0 is greater than or equal to 6. This is false, right? So that tells me that this point right here, this origin, is not in my solution set. So I don't want to shade the side containing it. I want to shade the opposite side. I want to shade above. So the solution set to this linear inequality is all the points on the line and everything I shaded in turquoise. Let's solve another problem. For our second example, we have 3x minus 4y is greater than 0. Again, I can't really visualize what this looks like until I solve for y, so let's do that. I have negative 4y is greater than negative 3x. I divide both sides by negative 4 to get my y all by itself. Because I divided by a negative, I flip the sign, and I get 3/4 x. Well, what's my y-intercept in this case? In this case, my y-intercept is 0. If I don't have a number listed, my y-intercept is 0. So we'll plot our y-intercept at 0. My slope is a positive 3/4, so my graph is going to look like it's going uphill. We go up 3 over 4. We can do that a couple times if we want. Over 4, right? This is y is less than. So because it's less than, the points on the line are not part of my solution. I'm going to connect this with a dashed line. Just make sure I can tell it's dashed on quizzes and checkpoints and things like that. Now I'm going to choose a test point. The problem is the test point I want to choose, my origin, is on the line, so I can't use that. I'd also think 1, 1's a little too close to visualize, so what if I do this point right here? When x is 0, y is negative 1. That could be a good point to use, but you can pick any point you want. Just pick one that makes the math a little easier. So here I've got 3x minus 4y is greater than 0. 3 times 0 minus 4 times negative 1 is greater than 0. That gives me 4 is greater than 0. That is true. So that means that this point is part of my solution set. So I can go ahead and shade that half because it's a true statement. When I do a check, that is another way for me to mark that, yep, that's true. the math worked, right? So this would be my solution set, everything I've shaded in turquoise. For our last example, we're going to see a compound inequality in two variables. I have 2x plus 4y is greater than or equal to 5, and x is less than or equal to 1. And means intersection. So I'm looking for where these two graphs are going to overlap. I'm going to graph x is greater than or equal to 1 first. Well, if I've got x equals 1, that's going to be a vertical line. It's greater than or equal to, so it's solid. And I could pick a test point, maybe right here, when x is 2 and y is 0. Is 2 greater than or equal to 1? Yes, that's true. So my solution is going to be over here. It's going to be this half. So I'm looking for where that intersects with what I'm going to graph in red. Maybe not red. That's a little angry. Blue, right? So I have 2x plus 4y is greater than or equal to 5, and I need to solve this for y. So we subtract 2x from both sides, negative 2x plus 5. I divide both sides by 4. Y is greater than or equal to negative 1/2 x plus 5/4. Now where's 5/4? Well, it's a little bit bigger than 1. So my y-intercept is 5/4. Let's put it right here. And my slope is negative 1/2. So I'm going to go down 1 over 2, down 1 over 2. I can do that as much as I want. And I'm going to connect that with a solid line because it's it's greater than or equal to. That means that all the points on the line are included in my solution set. And I can pick my test point to figure out how to shade. I'm going to pick 0, 0. So I have 2 times 0 plus 4 times 0 is greater than or equal to 5. 0 is greater than or equal to 5. That's false. So I need to shade above my test point, which was the origin. So this was my test point. Now, I'm looking for where these overlap. So that's going to be everything that's both green and turquoise together. So one option is I could erase very carefully what's not in my solution, right? That's one option. Or I could draw it in another color. You just have to make sure that when I'm looking at your work, I can tell that you know what's in your solution and what is not. And you might need to go back in and refill. Like for instance, I deleted a little bit of this line right here. And I should have taken away a little bit more right here. So that would be our solution set. That would be our intersection. If I said or, I'd be looking for union, right? Friendly reminder that, quick note in orange, or means union, and then I would have wanted everything my graph touched.